Hello everyone, welcome to my channel. So in this video, I'm going to talk about how to use Dartmouth method to define hospital service areas. So this is chapter 4 of our book, GIS Automated Delineation of Hospital Service Areas. So first, you need to make sure you can download data from my personal web page, and you need to install some Python packages. The instructions have been posted in my another video. You can go there and watch it and see how could you download the data and also install the Python packages. So in this video, I mainly talk about how to use the Dartmouth method directly. So first, we need ArcGIS Pro. Open ArcGIS Pro and then create the map. Create a new project. Let's see, we can set a name HSA book and then CW1. And then you can specify your location. If you want to change it, just click the browser and then specify to the path of the path that you want to save your project. And here, create a new folder for this project. If you want to check or uncheck, both are fine. So here we just use the default location and also check create a new folder for this project. And then we click OK. So we can create a project. It's empty. I only have the two maps, the top map and here shade. So we need the catalog. We could go to the folders, right-click the folder, and then add folder connection. Go to the path that you save the data, Florida folder, and then click OK. And then you will see when we expand the Florida folder, we can see there are several files. This one, FLMD, public transit, this is used to estimate public transit time. And the OD flow data is just like a flow data. You can go inside, take a look. So the results are all of the results I implement in the HSA book. And then scripts, these are Python scripts used for the tools. And this is our data, FL HSA geodatabase. You can see there are several hospital fire and also flow data, zip code area, zip code points, and some other original HSAs and HR that Dartmouth defined in the 1993. And also we could see the FLNTWK geodatabase. This is a lot of work in the Florida. And then Google Map API Pro is used to estimate the travel time using the Google Distance API. HSA Delineation Pro, this is our main tools. Half model is use half model to estimate flows, or say we can use this is mainly in the chapter 5. And this is a spatial adjacency matrix. It's used to adjust the spatial adjacency matrix. That's why I say append. ODO flows, this is used for estimate spatial behavior of cancer of patients to seek the inpatient care. And requirements.txt, this is used to install the Python packages. And the last one is to estimate public transit time. So these are the data in the Florida folder. So right now, we need to use HSA Delineation Pro, the .tbx. So in the catalog, we have the toolboxes. We right-click toolboxes, we add toolbox. And then we go to the Florida folder, go to the HSA Delineation Pro TBX, and then click it, choose OK. And then we can see we can load this tool. So we see build a spatial adjacency matrix. This is mostly used to build adjacency matrix to ensure your HSA are spatially continuous. And the calculate regionalization indices. So this is mainly used for calculate localization index, travel type, population, compact list, or some other indices for either HSA or HRR. Especially this is very useful. Suppose you already have the HSA boundary layer, and then you have the flows at the zip code level, and those zip codes are used to define the HSA, and then you can use this tool to calculate the characteristics of HSA based on the flows at the zip code level. And for consolidated flows at HSA level, suppose you have flows at zip code level, and then you have HSA, and right now you want to define HRRs, so you can aggregate your flows at the zip code level to the HSA level. And Dartmouth method HSAs and HR, you can see this tool could be used to define HSAs or used to define the HRRs. And network community detection method, there are two methods, SC-Delineating and SC-Loven. So I already introduced how to use this tool in my another video. So if you are interested about the network community detection method, so you can go to that video, take a look how to use this tool. So in this video, I will talk about Dartmouth method. So before you start using this tool, make sure your path is correct. Right now I have the TBX here. Make sure the path is okay. So we can go to the tool properties. There is some general. These are some definitions, and then they have a toolbox path here. And parameters, just like some parameters to define the tool label, lane, data type, and also type. You see some type are just required, which means you need to input the values for the parameters, and also direction, category, filter, dependency. So if you are not familiar with this part, don't worry. Don't need to go to this tool, this properties. You just need to ensure your path is correct. Okay. So we can click OK here, and then we double click Dartmouth method, and then we can enter this interface. So in the input polygon layer, this is usually for zip code, and the unique ID field, just a unique ID field for the polygon layer, population for the polygon layer. Population field is optional, which means if you have population, you can specify this parameter. Otherwise, you don't need to do that because it's optional. Input h5, this is only flows, original ID field, destination ID field. These are reference to, suppose right now we are working on the HSA, so the original ID field could be the zip code ID for the patients, destination ID field for the hospitals. So the origin ID and destination ID, they should be identical to the unique ID field. Service flows, which means how many patients or how many services patients receive from their hospitals. Distance or travel time, this is how long the patients will travel to the hospitals. So it's optional. You could see the delineation method. We have Dartmouth method. We also have the half Dartmouth method. So input a spatial adjacency matrix. You may notice in this tool, this field is required. So in the network community detection algorithm, you don't need to use a spatial adjacency because sometimes you don't want to input the HSA that are spatially continuous. But for using the Dartmouth method, you need to specify spatial adjacency matrix. This could be generated by the build a spatial adjacency matrix. Threshold size, the default one is 1000. If you want to change it, that's fine. But you need to make sure when you specify the threshold size, you need to specify the population field because this one is closely related to the population field. And the minimum localization index, this is used to capture the localization utilization rate, which means the more people stay local for the healthcare, the better. So localization index is actually a ratio of the service volumes within the HSA divided by the service volume originating from the same HSA to any other HSAs. So the higher ARI is more favorable because that means more people are staying local for the healthcare. And the output type, you see the dissolved one or non-dissolved one. Dissolved one means your final result will be HSA. Non-dissolved one, which means based on your input polygon layer, there will be additional attribute specify which HSA your polygon layer, each polygon in your polygon layer falls into. Okay, so this is the interface of the Dartmouth method. I think I need to introduce a little bit about the data we want to use. So in this tool, we need the zip code, and we also need the audio flows. Okay, so the audio flows is aggregated as a zip code area. So we can first take a look at the zip code area. So this is a zip code, just the 5 digits. And a Zoom ID is a unique ID. Right now we have 983 records, which means the Zoom ID ranges from 1 to 983. So make sure your Zoom ID start from 1. Okay. So X coordinate, Y coordinates, they are population weighted centroid as a typical layer. Because using the population weighted centroid is more accurate than the geographical centroid, because for the unpopulated areas, especially the rural areas, if you use a geographical centroid, maybe it's not very accurate. And the population is a population for the each zip code, and population density, this is just for mapping. And one thing you need to be careful, okay? So when you create a zip code area as your very basic geographic unit, make sure when you use the Dartmouth method or even network community detection method, don't use object ID, because this will cause the conflict. And then you will get some errors. So make sure you create a separate, like a Zoom ID, even though you could have the same value, but you should give a different name for the unique ID. So this is one thing you need to be careful. And then for the audio flows at the zip code level, so we can go inside, take a look. So this is a patient zip Zoom ID. So this ID is identical to the Zoom ID in the zip code area. And then second one, hospital Zoom ID is also identical to the Zoom ID in the zip code area. These two, the patient zip Zoom ID and the hospital Zoom ID, they're unique. And for here, I think the maximum value is 983, and the hospital Zoom ID, I think is it's the same. Okay, it's the same. And the hospital zip code is just the zip code for the hospitals. X coordinate, Y coordinate, they are identical to these two films in the zip code area. And the patient zip code is just 5 digits, and is also identical to the zip code in the zip code area. And then we have the hospital X MC, hospital Y MC. This represents the mean center of the hospitals in the zip code. The mean center of the hospitals in the zip code. So we know that one zip code may have 0, may have 1, 2, 3, 4 hospitals. So we use the mean center to represent location of the hospitals. All flows represent how many services the patients receive from the hospitals. And you see there are some records have the 0 value. So when we use the Dartmouth or network community detection algorithm, these 0 values will be removed. But here, because in this book, we use these audio flows also for some other chapters, that's why we keep 0 values here. Okay, so this is for composite, like Zoom IDs of the patient Zoom ID and the hospital Zoom ID. Total time minimum. So this is a total time. This is like how long the patients travel from their home, or say the residence to the hospitals. And this unit is minutes. And then this protein is mainly for half model. And then population means how many population in each zip code. Number of hospital beds here, potential, maximum potential, some potential probability. These are mainly for the half model. This is estimated flows by the half model as well. So in this video, I think we mainly need to use patient Zoom ID, hospital Zoom ID, and also all flows and even the trial time. So when you create an OD flow, suppose right now we have the patient Zoom ID 1 and hospital Zoom ID 20. And then if you have additional record like 1 or 20, and then you have the different number for the flows, you need to merge these two rows together to be one row. So that means when you create the OD flows, make sure there are no duplicate for the patient Zoom ID and hospital Zoom ID. So if you have the duplicates values for these two pairs, for the pair of these two films, make sure you need to merge them. Okay, merge them. Suppose if you have like 133, and then if you have additional row 133, merge them together. If you have 3, 4, 5, you can do all of these. How could you do that? You just right click and then do summarize. Okay. And then you can create a new OD flow tables. So these are for the data. And I want to mention one thing here in this video. We just talk about the zip code area and also the flows as a zip code area, because zip code is the most feasible geographic unit, especially for health data. And if you want to do delineation of the service area, like all functional regions for some other studies, even urban planning, transportation, and then you want to change the geographic unit, you can do that. You can create like a census tract, a census block, or grid, or a county, or some other geographic units, and then you need to make sure your OD flows are aggregate at those level. For example, if you have like census tract layer as a very basic geographic unit, and then you need to make sure your OD flows will be at the census tract. Okay, so this is the data, and then we can go to the tools. We just double click Dartmouth method, and then we input the polygon layer. This is the zip code area. Unique ID is a Zoom ID. And then we could specify population and input edge file. We need to go to the original data path, and then we go Florida HSA, and then we click audio flows, click OK, and then we go to original ID. This is the patient zip Zoom ID. Destination ID is hospital Zoom ID, and service flow field is all flows. And then we can go distance. Here we can choose the total time minimum. For the delineation method, we just use Dartmouth method. This is the default. And then you see we need to specify spatial adjacency matrix. Right now, I just suppose I already created the one. I can go to the result, and then I can select this one. This is a Florida polygon. Adjacent up. This means the polygon means the zip code. I can use this file. Okay, so .mpz is a file format to store the array data, which is very efficient, especially when you want to deal with the large matrix. And the .mpz is actually a file format provided by the NumPy package. So if you're familiar with the NumPy package, you probably know what is .mpz. Okay. Clicking OK, and then we see we have the threshold size. Like what I said, when you specify this one, you need to make sure you specify the population field. And then the minimum organization index, we can specify nothing there. That means we don't need this constraint because this is optional. And then output type, we could use the dissolved, and then we change our name, Dartmouth HSAs. So make sure your outputable coordinator could be a place that you can find. Okay, and then we can click around. See, it's very quick. So after you run this tour, you can see the two options, view details and open history. And we can click the view details and then we could go parameters. These are parameters you already set in this tour. So I think for the parameters, most of the time it will be very useful if you want to trace back to see whether all of the parameters are correct. And then we have environment, there's nothing there. And then message, we can see the message, there are 7. And there is some information here. First, how many zip codes you used 183, and total population is this one. And then we see total number of flows is 37, 180. So you may see this is more than the only flows here. Why this happen? Because we use the non-zero flows. Okay, so we can choose all flows and then greater than 1. Could see how many flows we use. Actually, we use the 37 and 180, right? So because we only use a non-zero flows. And then we see this is the number of source volumes. You can even choose all of the 37, 180, and then you go all the flows, right click and do statistics. And then I think you will see you actually have 2.3 million, the same number of the service volumes. Okay. And then we just clear the selection. And then we see we actually have 208. This means 208 zip codes that have hospitals. And then you see we impose the population constraint, but we do not impose the AI constraint. So it's okay. And then the Dartmouth method delineate 136 HSAs. Okay. And then I think this result should be identical to the result we get in the book. And then we see HSA. We right click Dartmouth DHSA DHAS1 and miss S. So it should be okay. So after you run this tour, the result will be automatically loaded in the contents pane. So we right click, click attribute table, and then we can can see what attributes the HSA has. So we have HSA ID, I think 1 to 136, and then count zoom ID, which means how many zip codes for each HSA. Population, which the population for HSA, and then we have ARI. So definition of ARI is the ratio of the total service volumes divided by the total service volume originating from the same HSA to any other HSAs. So you can see the ARI value always ranges from 0 to 1. Okay, the higher the better, which means more population are more likely to stay local for the healthcare. Estimate time, this is weighted trial time, calculated by the trial time and also flows. Number on D zoom ID, which means the number of destination zip code for each HSA. You see the value ranges from 1 to 7, which means this satisfy our expectation because we want to make sure each HSA has at least one hospital or say one destination zip code. Compactness is a correct ratio of the parameter and also the area. It's just like to measure the regularity of the HSAs, and a low value means more compact, which means a high value means less compact. And we always expect our HSA are more compact. So this is some characteristics for the HSAs. And now we see we get 136 HSA, and we can right click, click symbology, and go to unique values. We can choose a different color scheme, show all, and then we see we can choose more colors, this one, and then we can add all of the HSAs, and then we can see how they look like. So you will see most HSA are spatially, all of HSA are spatially continuous. Okay, this is the result. And then you will see, I want to talk a little bit more about the spatial adjacency. So you see here, these two, actually these are two, probably at least the two zip codes, this one, and then this one. Right now they become one HSA. Why? Because I use the spatial adjacency matrix, and even use that, couldn't guarantee they're connected, but because I adjusted the spatial adjacency matrix, I make sure they are connected, so they could form one HSA. So even for here, it's the same story, okay, same story, because I adjust the spatial adjacency matrix. So we can talk about it later. So this is a dissolved one. If you say, oh, no, I don't want to dissolve, I just want to change, let's see, 2. And then I can click around again. See, it's very quick. And then it only takes the 6 seconds. I think for our previous one, it only takes seconds to generate the HSAs. And then now you see the result is automatically loaded. And then we can go to the attribute table and see, we see 983 records, and then we have HSA ID. Okay, ranges from 1 to 136. So this is very useful, especially you have some characteristics at the zip code level. Suppose you have population, you have household characteristic, transportation, income, race, gender, education, and some other variables at the zip code level, and then you want to do further analysis or do like aggregation or do the statistic analysis, I think this layer will be very useful. So this is like a crosswalk file of the zip code and the HSA. Okay, so this is our dissolved or not dissolved, even though for 1, 2. So we can change the I think we also need to check, because in this scenario we use 1,000 population threshold, so we can check the minimum population we see is 5790, which means this value might be small. So we can maybe change to 1,000, and then we can dissolve a 1, and then we can choose probably 3, DHSA S 3. This is our new layer, and then we just click run. So you see it also runs very quickly. So we see we use the threshold like 10,000. So we can go to the new layer, see the attribute, see what is the minimum value. Now the population, the minimum value is just a little bit higher than the 10,000. Okay, 10,000. So that means this threshold size works, right? So and right now we can see we get 133 HSAs. So you can change the threshold size if you think you need to do that. And also if you think you want to compare with some administrative units, and then you know the minimum population for them, and then you can set up the threshold size. And then for the minimum localization index, you can do that as well. Suppose we want to set 0.5, and then let's see the new result. So 0.5 means half of the population stay local for the inpatient care. You see, this tool is very efficient, only takes a seconds. And right now we can see we get a 73, right? We get a 73, I should say. And then we go to the attribute table. First, we need to make sure the minimum population is at least 10,000. Yes, we get 40,000. And then we can go to ARI. We see the minimum value is at least 0.5. We get a 0.507, right? So this means the result satisfy our lead because we set these parameters. And then there are 73 HSA. So these are just the cases when you use a spatial adjacency matrix that I already created in the result. Okay. So if you have the data in some other study area, you need to build your own spatial adjacency matrix. So how can we do that? We can use the build a spatial adjacency matrix, double click this tool, and then go to zip code area. So unique ID is the zoom ID, and then adjusted is if you choose no. This is very basic. So we can choose no, and then we just let me create a new. Let me create a folder to store my result. Okay, test results. So here you need to specify a tour Florida and then a adjacency and .mpg. So remember, set the extension .mpg for your result, and then you could get click run. Sync should be very quickly. You see the review the details. You see only take 2 seconds, and then let's see, that already told you. So you get the MPZ file under this path, and also I generated a CSV for you to understand your result or check whether your result is correct. So we could go like here. I think I set up, see this one. So this is a CSV file. We can go inside, take a look. This is a Zoom ID, original Zoom ID. That's relation Zoom ID because they're connected. So their weight is 1. So if they are not connected, they will not show in this CSV file. Right? So this is a result how to use the build a spatial adjacency matrix to directly create a matrix. But for this case, let's see, I think here is more classic. So you see, this is one zip. Oh, sorry. I think I should go to the zip code layer. All right. So you see, this is one zip code. And then I think this is, okay. So this is one zip code. It's all right. So for here, zip code, and zip code, right? So these are not connected. And then we see there are rows, right? There are rows here. There are rows 700, and even road probably from this zip code to here. There is a row along this one. And then this is one cases, and also we can see from this zip code to this zip code, even though they are not physically connected, but there is a road 27 between them. Okay. For this zip code and this zip code, even though they are not physically adjacent, they have 18.4, which means especially for like some farmland or some forest, a river or lake, because for some reasons, some zip codes may not be spatially adjacent, but you can still create a spatial adjacency matrix to make sure they could be connected. Okay, so this is one case. And then I want to show you more because not only the farmland forest, sometimes because of the bridge, right? So for here we have the zip code, for here we have a zip code, and then there is a bridge actually connected with it, right? 275. But if you choose no, and then the tool will not know they could be connected because the man-made infrastructure. So if you could adjust them, make them connected, and then your result will be more will be better to represent what we see in the real world. And then for this one and this one, they are connected as well. This is by a highway. And I think I want to take, so this is also a case, zip code, they are connected by a bridge. And right now I want to show you one more case. I think that's especially happened in the island. So here, okay, so this is one zip code. Suppose these are two zip codes, okay? So there is the island zip code. This is another zip code, even though they are physically not connected, but because the people live in this island, they can take water transportation to go to the mainland for the healthcare. So in this case, we need to make sure this island should be connected with the mainland, okay? So in this case, because there's only one zip code in the mainland, so we could only, the best option for us is still this zip code. But if you say we have several zip codes in the mainland, which one should we choose? We choose the nearest one, okay? The algorithm will help you automatically to identify the nearest one, so you don't need to worry about this part. What you need to do is just choose yes for the adjusted, and then you need to create the input adjusted adjacency file, okay? So in this case, we could go to the result. I think no, go to Florida folder, go to this one. So this is the file I created. Okay, I created because I need to adjust the adjacency matrix. So this is the original ID. This is the destination ID. So this means this ID and this ID, they could be connected by the physical road or water transportation or other transportations. Okay, or just the physical road bridge because they are connected. So they should be shown in this table. Okay. So if two zip codes, if you check they are not connected, they will not appear here. Okay. So you can see we have 34 pairs. And then we can try to see, we can input adjusted adjacency matrix. Could go to FLPLGN, ADJ, and then append dot CSV, we collect. And then we can change the, let's see, we can change maybe 5. And then we can run it again. And see, you see the result is really quick, 2 seconds. And then because we have this result, right? We know there is a path here. We can go to this path. This is where we save the result. Think it's not here. Let me see. Yes, it's here. So it's okay. Just like this is the CSV I generated simultaneously to help you to identify, to check, double check whether this is correct. Origin zoom ID, destination zoom ID, and weight. And then let's see how many records they have. They actually have 5216 records. Okay. So this is the adjusted one. I think this is not adjusted one. So we could go to scroll down to the bottom and see we have 5148, right? So we can calculate, this is 5216 minus, that one is 15148. Then we get 68. Why is double? Because when we specify the adjusted matrix, so suppose the adjusted matrix is 1, 2, and then we get 2, 1. Okay. That's why the result is double. And also you can plot the spatial adjacency matrix, just like right now, because this is a zoom ID. If you have XY coordinate in this table, you can join, and then you can join the dzoom ID and the hospital mean center to the dzoom ID, and then you use wedge. You use XY trend line to create a feature, and then you can double check whether those zip codes are really connected. So this is really useful. And also, when you create a spatial, after you create a spatial adjacency matrix, right now, we can go Dartmouth method, we can impose the spatial adjacency matrix, recreate it. And before, when you do that, make sure always, okay, because there are several things. The zip code ID here in the build a spatial adjacency matrix is identical to the unique ID here, and will also be identical when you use not dissolved. So the zoom ID is a key. Okay, make sure your zoom ID start from 1. Okay, make sure they are unique when you use the zoom ID for the zip code area. If you want to use some other layer, make sure they are unique as well. Don't use the object ID. Okay. So I think that's the way how to use the HSA to create this method to create HSA. If you are interested to create HR, just make sure your input polygon layer is HSA, your OD flow is at HSA, and then other parameters setting are just the same. Okay. And then your result will be loaded automatically to show how your HR look like. So this is a Dartmouth method.